Hey everyone, welcome, and I'm glad to see that you're back for the second video after our first video about what is calculus. Today we're starting in on the textbook itself, and we're starting in section 1.1, which is called Functions and Change. So you've probably learned about all different kinds of functions in your math classes before calculus. Probably the first one you learned about many years ago were linear functions or lines, and that's what we're going to talk about mostly today. But you probably also saw parabolas, exponential functions, logarithms, and many other types that are going to pop up in our calculus class this semester. Before we talk about lines, I want to talk in general about functions. There's lots of different ways that you can define a function. Really, a function is just a rule, a predefined rule that transforms some numbers into other numbers. And I like to think about a function as a black box, meaning a box that you don't know what happens inside of it, that you feed input numbers into the black box, and it does something, some kind of magic to that number, and on the other side, you get an output. So a function is just some way of taking input numbers and transforming them and getting output numbers. The really key thing that makes a function is that you can only get one output for each input. You can't get two different outputs for the same input. It always has to be the same. So if you've got your function, your black box here, and you put in 3, that's your input, and you get output 5, then one way that we write this is f of 3 equals 5. So when you see this notation here, f of, that's the input, and the 5 is the output. And again, the way we say that in English is f of 3 equals 5. The key is that if that's the case for your function, then f of 3 has to always be 5. It can't be 6 sometimes and 5 other times. Here's the book's definition, which is pretty similar. The book says a function is a rule that takes some numbers as inputs and assigns to each of them a definite output number. When they say definite, that's their way of saying that it can't change, the way I said. Now, a couple extra definitions here. The set of all of the input numbers is called the domain of the function. So the way that I would phrase that is that's the set of all valid inputs. Those are the things that you're allowed to feed into your black box. The other thing we're going to define is the range. The range of a function, these are the set of numbers that come out of the black box. So these are the set of outputs. So the domain, that's the set of valid inputs, and the range is the set of outputs that you actually get. Now the domain can be a little bit tricky. Sometimes the domain is explicit, and what that means is that when we define the function, because we can define any kind of function we want, we specifically say what the domain is. And if we specify what the domain is, then that's it. That's very easy. That's an explicit domain. Other times, the domain can be implicit. Implicit means that we're not going to specifically say what it is, and so you assume, in that case, that the domain is all of the real numbers that make sense to plug in. So for example, you know that you're not allowed to divide by 0. So if plugging in a number forces you to divide by 0, that's not valid, so that can't be in your domain. Another example is you know that you can't take the square root of a negative number. So if using some input forces you to take the square root of a negative number, that can't be in your domain. We'll see examples of those in a minute. Before those examples, I want to point out a couple of notes. We've been calling our functions f and f of x. That's just a common name for a function because function starts with f, but it's equally valid, and we will do this often, to call them other things like g of x or h of x or capital B of x, or even use Greek letters sometimes like alpha of x. The actual letter that you use is just your choice. Another thing that you're going to see, especially because we're drawing lots of functions in the xy plane, is we'll write y instead of f of x. So for example, if we're considering a function like maybe f of x equals 3x plus 5, that's an example of a line, as we're going to see in a little bit. The book might also, and we might also write this sometimes as y equals 3x plus 5. That's just to emphasize that we're going to plot this on the xy plane. Oh, I'm in the way a little bit. Still getting a little used to this technology here. And even sometimes these will be combined, and you'll see y of x. The of x is just meant to be a little mental reminder that, oh, this depends on x. It's not its own independent thing. OK, let's see our first example. So here's our function, f of x equals x squared minus 3. Now, I'm defining the domain. So this is an example of an explicit domain. When you define the function, and here I'm the one defining this function, you're allowed to specify the domain. So this is this function on the x values between -2 and +1. So here we have a Desmos graph to go into. So let's go into the graph. What you see here is the graph x squared minus 3. Now, this is showing the graph for all of the x values, not just the ones that I said from -2 to +1. So in Desmos, you can specify that you want to restrict the domain like this. And so here now you see in blue the part of the function between -2 and +1. So let's think about this. If I plug in -2 into the function, the black box of this function, x squared minus 3, says I take as input some x, I square it, I subtract 3, and I send that out the other end as my output. So when I plug in -2, I square it, that's 4. I subtract 3, that's 1. And if you look at this graph, if we can zoom in, that first point is at -2, 1. So it's -2 on the x-axis, and it's 1 on the y-axis. And in fact, if we want, we can even label that point. We just have to bring our little slider over here. And there we see -2, 1. Now, as we slide from left to right, we have points that go negative. We've got this lowest point here. That's at 0, -3. Now, again, let's try to make sense of that. If we plug in 0, our black box says take your input, square it. Well, 0 squared is 0. And then subtract 3, and you get -3. So there we see 0, -3. And then we come up the other side until we reach this rightmost point, which is 1. And you can check on your own that if you plug in 1, what comes out the other side is -2. So we've got the full graph in red and the restricted part in blue. Now let's write, like we are going to do this for each of our examples, let's write the domain and the range. Now in this case, the domain is really easy because it was explicit. So the domain is just x between -2 and 1. Now range, on the other hand, these are the set of numbers that come out. In terms of a graph, let's go back into our graph. In the terms of a graph, the range is all of the y values that we hit. And again, we're not looking at the red part, we're just looking at the blue part, which is the part with our restricted domain. So which y values do we hit? Well, the smallest y value we hit is at the bottom, 0, -3. Oops, our blue line disappeared. We hit -2 twice. We hit on the left and the right. As long as we hit it once, that's fine. What's the largest y value that we hit? It's 1. So the smallest is -3, the largest is 1. And that means our range here is x between -3 and 1. So let's draw a little graph over here on the side, just so we have it. So our domain was -2, so 2 on the left, to 1 on the right. And we found that at -2, we had height 1, so that's the point -2, 1. At 0, we had height -3, so 0, -3. And then at 1, we had height -2, 1, -2. And our function looked like that. Okay, so that was our first example. In this one, the domain was explicit, so we just defined it. Now in this next example, the domain is implicit because I haven't defined it. And that means that implicitly, the domain is all of the real numbers that make sense to plug into this function. So our function is the square root of x minus 2 plus 5. So let's think about what happens in the black box. We take a number x and we feed it into our input. And what does the machine do? Think about order of operations. First it subtracts 2. Then it takes the square root of that. And then it adds 5 to that. So let's plug in a number, just kind of for some practice here. Let's see, what's going to be nice? Let's do q of 11. So when you plug in 11, what happens? Well, the first thing we do is 11 minus 2, and then the square root of that, and then plus 5. So 11 minus 2 is 9. That's why I knew this would work out nicely, because the square root of 9 is easy. The square root of 9 is 3, so this is 3 plus 5, which is 8. Okay, now let's go into our graph and see it plotted for us. Now you'll notice this does not exist all the way to negative infinity on the left. It kind of just starts, and it starts at the point 2. Now that makes sense because if you look at the function here, we are taking the square root of x minus 2. So what would happen if I plug in 0? If I plugged 0 into the function, I would have the square root of -2, and you can't take the square root of a negative number. So 0 can't be in the domain. If I tried to plug in 1, you'd get the square root of 1 minus 2. That's -1, so 1's not in the domain. The smallest number in the domain is 2, because then I get the square root of 2 minus 2, and that's okay. The square root of 0 is 0. That exists. But anything smaller than 2, I'm going to be taking the square root of a negative number, and anything larger than 2, I'm taking the square root of a positive number, and that's fine. So the domain is 2 all the way to infinity. This is going to increase forever and ever, and it does get less and less steep, but it will keep increasing. Okay, so that is our domain. We'll come back to that for the range in a second. So we just discovered the domain is all x values between -2 and infinity. Now you don't really write the infinity here. That part's not necessary. You can just say all x such that -2 is less than or equal to x. Okay, now the range, remember, that's all of the output values that are possible. So let's go back into our graph here. Based on the graph, it looks like the smallest value we can get is right there at 5. And that's when we plug in 2, we get 5. And that makes sense because that's the square root of 0 plus 5 is 5. So we can't get anything less than 5. Now it turns out, as we kind of saw just by scrolling around, that you can get anything bigger than 5. It might take a while, but you can get there. So we see this from the picture, and for now we'll take that as good enough. So the range, this is everything from 5 and up. So we can just write this as x greater than or equal to 5. Okay, so this one had an implicit domain, but we figured it out by looking at the function and saying, well, what could go wrong? What possible bad things do we have to watch out for? And the main one here was we had to make sure we weren't taking the square root of a negative number. And by ensuring that we only allow plugging in, oh, this is a typo here. That shouldn't be -2. That should be +2. You were probably all yelling at your computers there. +2, because if you plug that in, you get 0 under the square root. And if you plug in anything less than that, then you get something negative. Okay, moving on, I've got a little side note here on interval notation. Now, this is probably something you saw in pre-calculus, but just in case you didn't, I want to make sure that we're all on the same page. Interval notation is a nice compact way of writing intervals, and on the previous slides, we have been writing intervals. Here were some, and this was an interval that had 2 endpoints, and so on. The key is that we look at the 2 endpoints, something on the left, something on the right, and we put them in either square brackets or parentheses. And what tells us which one to use is you use a square bracket when that endpoint is included, and you use a parentheses when it's supposed to be excluded. So let me give you an example here. We'll go down this list and write them all. If we're looking at the interval of, this is all real numbers x, this first one here, all real numbers x that are greater than or equal to a and less than or equal to b, we would write that in interval notation as just square bracket a, comma b, closing square bracket. We have the square bracket because it's included, and we know it's included because we have that equal to part. In this second example, these are all real numbers x strictly greater than a, so a is not included, and less than or equal to b. So that means we have to use a parentheses on the left for a because it's not included, and a square bracket on the right for b. The next one is kind of the reverse. A is included, and b is excluded. And in this fourth one, they're both excluded. So that's a, comma, b. Now these last four examples, these are examples that only have one endpoint. So for example, x is greater than or equal to a. So if you think about on a number line, that means a is included, some point a, and everything to the right. So maybe let's draw a little number line here to help us visualize that. That means somewhere we have a, and the valid values are everything to the right. Well, that's hard to see. Let me pick a different color. Everything to the right of a, including a itself. So that tells us that we can write this in interval notation, putting a square bracket a on the left, because the picture tells us that a is the left endpoint. And to show that it goes all the way to infinity on the right, we do infinity. And I have a note here that says with infinity on the right or negative infinity on the left, you always use parentheses. That's just kind of a convention. So that one looks like that. The one right below it, this is x strictly greater than a, so it's the same kind of example, except the point a is not included, so it gets a parentheses. And on these last two examples, they're similar. We've got a point b, but the valid points are now everything to the left because we have x less than or equal to b. So it looks like that. So this goes from negative infinity on the left to b inclusive. And the example right below it goes from negative infinity on the left to b exclusive. OK, so the key here is square brackets when you include the point, parentheses when you don't. Infinity always gets parentheses. And you just have to be careful with some of these examples here that you think about, is the point I have a left endpoint or right endpoint? OK, another example of a function. This one uses something we haven't seen yet in this lecture, and that's the cubed root. So that's what this here is. This is the cubed root. Square root, let me just remind you, if y equals x squared, the way you would solve for that is x equals the square root of y. So squaring and square root are kind of opposites. And there's usually a plus or minus here, but you can ignore that for a moment. The cubed root bumps that up by 1. It says if y equals x cubed, then x equals the cubed root of y. So the cubed root of y is the number that if you multiply it by itself 3 times, you get back y. So our function here is negative cubed root of y. And once again, we have a nice graph of this. At 0, it has value 0. And that makes sense. If I multiply 0 by itself 3 times, I get 0. So that tells me the cubed root of 0 is 0. And negative 0 is 0. So nothing interesting here. To the left, it's positive, and to the right, it's negative. And you can just kind of see these points going back and forth. So this is what the function does. Now, just based on the picture, it looks like we know what the domain is. It looks like the domain is all real numbers. Now, if you know about the square root, and well, I guess we just talked about the square root, in that case, we have to be careful not to take the square root of a negative number. But in this case, it doesn't seem we have a problem. So let me just remind you why that is. If you think about, let's say, what's the cubed root of 8? Okay, the cubed root of 8 is 2, and that's because 2 times 2 times 2 is 8. On the other hand, if I do the cubed root of negative 8, the square root of negative 8 doesn't exist, but the cubed root of negative 8 does, and it's negative 2. And that's for the same reason, because negative 2 times negative 2 times negative 2 equals negative 8. So you can take the cubed root of negative numbers, but not the square root. So our domain is all real numbers. Everything is valid. And this isn't exactly one of the examples that we saw on the last slide, but you can probably figure out that the way you would write this interval is negative infinity to infinity. And we said that infinities always get parentheses. So we just put parentheses, parentheses on both sides. Okay, let's look back at the picture for a minute to figure out the range. Now this one is a little bit hard to tell, but you can take my word for it for now, or remember some of your pre-calculus about roots, that this is actually going to reach all real numbers. It's getting there very slowly. Remember, the square root increased slowly. The cubed root increases even more slowly. I wonder how far this is going to let me scroll. But it will eventually get to all real numbers, positive on the left-hand side, and on the right-hand side, it will let me get to all real numbers negative. So I get the positive real numbers as I go to the left, and I get the negative real numbers as I go to the right, and eventually I get all real numbers. So our range, just like the domain, they happen to be equal here, is negative infinity to positive infinity. Okay, so we looked at some examples of functions, and now we're going to talk about a very particular type of function called a linear function. This is just a fancy way to say straight lines. So a lot of this might be review for some of you. Maybe it's new for some people. I want to make sure that we're all on the same page, though. So let's start from the basics. Every line has two important things. It has a slope. The slope tells you how fast that line goes up or down, steep or shallow. And it also has a y-intercept, which tells you where the line crosses the y-axis. So looking at this example, here's an example of a line. I drew 2 points, 0, 1, and 5, 2, and then I connected them with a line. So let's start with the y-intercept, because that's actually much easier here. The y-intercept is the place where it crosses the y-axis. And we see that just because we happen to have it drawn for us. It crosses at 0, 1. Now the 0 is always going to be there because it's the y-axis, so it's 0. The interesting quantity is the 1. That tells you the height at which it crosses. So the y-intercept is 1. The slope, we have to do a little bit more work. The slope we need to measure, if I go over 1, then how far up do I go? So one way that you may have seen that written before is as rise over run. That's just a way of saying how quickly you go up divided by how quickly you go over. So let's look at these 2 points. If you go from one point to the next, how far do you rise? Well, we go from 1 up to 2. Okay, I drew it at 3, but I labeled it 2. So let's fix this. Let's make the picture correct. That's a different green, but that's okay. We go from 1 to 3, so that means we've gone up by 2. And how far over did we have to go in order to go up by 2? We had to go from 0 all the way over to 5. So in order to go up by 2, we had to go over by 5. And so now we have our slope. Our slope is 2/5, and our y-intercept is 1. Here's the book's definition. It's basically the same thing we just said. the key is that they're now writing a line in this very particular form. They say a linear function has the form y, or f of x, we know that we can use both of those, equals, and this is the interesting part, b plus mx, where m is the slope, and b is the vertical intercept, or the y-intercept. So this is another way to say y-intercept. And the book will write it in this order, b plus mx. Most other textbooks will write this as mx plus b. Of course, that's the same thing because addition can be done in either order, but I just wanted to let you know. So let's take that line from the last slide and write it as a function. We calculated that the y-intercept was 1. That was pretty easy. And we calculated that the slope was 2/5. And we fixed our point here. And so that's all the information that we need to write this line as a function, because this tells us exactly what form to do. We do the y-intercept, so that's 1, plus m, that's the slope, 2/5, times x. And this is our function, 1 plus 2/5 x. So when you read that out loud, it almost feels like you're just describing a line. You're saying you start at 1, and then for every x you go over, you go up 2/5. So you start at a height of 1, and then you go over by 1, so you go up by 2/5. You go over by another 1, you go up another 2/5, and so on. And the same in reverse. If you went left by 1, you would go down by 2/5, and so on. And that's what makes a line a line. Let me show you a more interactive example. Now again, you don't have to worry about what all the things on the left-hand side are doing, but what I want to point out here is, and you may have heard this before, that 2 points determine a line. If I put down any 2 points, as long as they're 2 different points, I can draw a unique line between them. And from those 2 points, I can calculate the slope of the line, the y-intercept of the line, and therefore the function. So I'm going to look at 2 points here. One of them I'm calling c comma d. So it's got an x value of c and a y value of d. And the other one I'm calling r comma s, just names that I picked. And the Desmos graphing calculator lets me slide these values around. So I can change the x value of the first point and the y value of the first point, as well as the values of the second point. And no matter what I pick, it's calculating for me the slope. So you can use this calculator to actually graph some things as well as calculate some values. So for these particular 2 points I picked, let me pick ones maybe a little bit nicer. Let's say -2 comma 1 and 5 comma 4. Then it calculates the slope for me. It only does it numerically, not as a fraction, but it's about 0.428. It also calculates the y-intercept for me. Now, I haven't showed you how to do that yet, but we'll see that in an example later. That's about 1.857. And that kind of looks right if you zoom in, that could be about 1.857. And so it plots the line. So what this is doing for me is I'm picking the points, it's calculating the slope, it's calculating the y-intercept, and then it's plotting this blue line here on top of it. So we're kind of seeing confirmation that our formulas work. Now, for all the topics in the book, all the sections, the book has a lot more examples than we have time to go over in these videos. Some of the examples that I'll do are ones that I made up, and some will be from the book. But you should always go back and look at the book's examples for more practice. And I will try to point out when there are some topics in a section that we are not covering, either because we're going to skip it entirely or because we'll come back to it later. So for example, in section 1.1, there are little bits about increasing and decreasing functions and proportionality. And you're welcome to read those on your own. We'll come back to them later, but for now I've decided to skip them. So this is the end of the main video for section 1.1. For all the sections in the book, my goal is to make one main video like this one that gives you the important definitions and a couple easy examples. And then I'm going to make a second video where I pick some of the exercises in the textbook from that section and just work them out with you from scratch. So you should always watch both of them, the first one to give you the main ideas, and then the second one to give you some practice on your own. So you'll be able to try to work out the problems alongside me for some extra practice.